Alright, welcome to this mini lecture on analysis of variance. And let's just jump right into it. So when do we use analysis of variance? And the answer is that we always use ANOVA or analysis of variance whenever we want to test for differences among more than two means. So consider the following example. Assume that 4 people eat 3 different cookies, A, B, and C. And they evaluate their taste on a scale from 1 to 10, with 10 presumably be the better taste. So then the null hypothesis is there is no difference anywhere between A, B, and C, and the alternative is there is at least one difference somewhere. So what is the difference to a two-sample t-test? Of course, we could also test whether there is a difference between cookie A and cookie B, between cookie A and C, or between cookie B and C, and then we could conduct 3 different two-sample t-tests. Yeah, that would work, and maybe it's feasible if you have a few groups that you need to compare, but such a strategy is generally more cumbersome. And so therefore we use ANOVA, and again ANOVA stands for analysis of variance, and I want to first get to the intuition of analysis of variance. So when it comes to analysis of variance, there are 2 sources of the variance of all those observations. And the variance could be largely between the groups. And I want to illustrate that in Excel. And let me just open Excel quickly. And let's say we have 4 groups or 4 observations. A, B, and C. Okay, so when it comes to analysis of variance, we distinguish basically the total variance and then the between group variance and the within group of variance. Consider the following example, just an extreme example, 1, 1, 1, 1. So all the 4 test persons don't like cookie A very much, and all test persons, they give cookie B a 5, and all 4 test persons give cookie C a 10. So now there is no variation whatsoever in each group. And all the variation comes from between the groups, right? So that suggests whenever the variance between the groups is very high, but the variance within each group is very low, then we probably find a meaningful difference between A, B, and C. And let's just compare that to another example. Let's say we have those observations and we have maybe 2, 8, 4, and 6, and here we have maybe 6, 2, 4, and 8, and here we have maybe 8, 2, 4, and 6. So those are always the same 4 numbers. So there's really no difference in the averages between each group. So that suggests that all the variation comes from within the group. But there's really not much difference in the variation between the groups because they have all the same mean. So that suggests then intuitively that we probably don't find a meaningful difference anywhere between cookie A, B, and C. So I hope that that brief example made it clear. So we have in ANOVA different sources of variance or variation, and so we have the total sum of squares, and the total sum of squares simply looks at all the differences of the overall mean. So what is the overall mean of all the cookies? Okay, so now let's see if we can calculate that, probably in our head. So we have a total of 12 observations in total. So the overall average, or the grand average, I call that x grand. Okay, so this is 3, 8, 11, 12, 17, 22, 23, 28, 34, 44, 54, 60. So 60 divided by 12, that is 5. Okay, so now what is now the total sum of squares? The total sum of squares are all the deviations from the 5 squared. So 3, the deviation to 5 is 2, so the first one is 4, 2 squared. Then we have a 5, so that's a 0. Then we have a 3, so that's again a 2 deviation squared, 4. Then 1 from 4, that's a 16 squared. Okay, so then the 5, that's again twice a 0. Then a 1, that's a 4 deviation squared, 16. Last one is again a 0. Then here the 6 is 1 away from the 5, 1 squared is 1. Then 10 is away from the 5, so that's 25. Then we have another 25. And then we have for the 6, that's 1 away, so that's a 1. So how I did make a mistake. So then the total sum of squares is 4, 8, 24, 30, 40, 41, 62, 67, 87. Okay, so that doesn't look something right. 2. So again 4, 8, 24, 30, 40, 41. Oh, plus 50, that's 91 plus 1, so that's 92. So no, that's correct. So that's 92. So that's the total sum of squares. We just sum up all the squared deviations from the grand mean or the overall mean. Okay, so then what is always a little bit difficult to calculate is the between sum of squares. At least if you try to calculate it individually, there's a formula for it, but it's a little bit complicated. So, but we need to know that the total sum of square is the sum of squared between minus the sum of squared within. So the sum of squared within, that's actually relatively easy. So that is just the sum of square from the mean of each group. So if we do here x bar for each group I or A, B and C, so here we have 3, 8, 11, 12, 12 divided by 4, so here we have a mean of 3. Then 5, 10, 11, 16 divided by 4, the mean is 4. 6, 16, 26, 32, 32 divided by 4, that's 8. Okay, so the total sum of squared within for, let's say, group A is, okay, 0, 5 minus 3, so that's 4. 0 plus 4, then again another 0, and 2, so squared another 4. Okay, so that is the total sum of squared within the group of A is 8. What about B? Okay, 5 is 1 away, 3 away, so that's 1, 2, and 9, that's 11, and okay, let's just write it down. So, and here I just forgot one number here to be accurate. So here we have a 0 plus 4 plus 0 plus 4. Here we have 1 plus 1 plus 9 plus 1. So the sum of squares within the group of B is 1, 2, 11, 12. And the sum of squares within group C, so now we have to relate everything to the within group average of 8 for group C. So that is 2 squared, 4, another 2 squared, 4, another 2 squared, 4, and another 2 squared, 4. So this is 16. So in this case, the so-called sum of squared within all groups is 36, which we have here. And we know that the total sum of squared is 92, so then we can calculate the sum of squared simply as the total sum of squared minus the sum of squared within, and the sum of squared within needs to be 56 then. Okay, so this is how we calculate it, and what we do next is we summarize that in a ANOVA table. And so what we do is we start with the sources of the variation. Between the groups we have 56. Then within the groups we had 36. And then the total sum of squares is 92. So 56 plus 36 equals 92. Then we have to average out the sum of squares between the groups over the degrees of freedom. So in our case, we had 3 groups or 3 cookies, A, B, and C. And then the degrees of freedom is the number of groups minus 1, which is in this case 2. So in other words, if I know that the sum of squares within the groups is between the groups is, let's say, 56, and I know 2, well, I know what the variation of the remaining third group must be in order to make it to 56. So, and then we average it out over the degrees of freedom. So the way you can think of it is that we essentially average out the variation per group, and the higher that is, the greater that variation per freely varying group is, well, the more can be attributed to the groups. So we average it out over the between groups, and then we get 56 over 2, which is 28. Then we look at the variation within each group, and the degrees of freedom is the total number of observations. In our case, that is 12, minus the number of categories or classes, the K. So that is 12 minus 3, the ABC. And again, the way you can think about it is, for example, if we know that the average in each group, if we know the average of each group, like 3, 4, and 8, well, then I can always ignore one observation within each group, And I know what the fourth observation will be if the average is a certain number. So then within each group of 4, 3 can always vary freely. But if I know the average of the 4 observation, I know what the fourth element or what the fourth observation has to be. So that means we have here 1 degree of freedom in group A and B and C. And so then we have 3 times, so we lose, so we have 3 times 1 degrees of freedom, but we have to subtract those from the total number of 12, and then we get 9. So we average out the within groups variation of 36. We divide it over the degrees of freedom, which is 9. And then we get 36 over 9, which is 4. And then we calculate what is known the F statistic. And so an ANOVA table typically yields an F statistic. And the F statistic is defined as the mean sum of squares between the groups over the mean sum of squares within. And again, the between groups variation goes into the numerator, and that has a certain number of degrees of freedom. Those are the degrees of freedom in the numerator, and here we have the degrees of freedom in the denominator. And in this case, our F statistic is 28 over 4, which is 7. And now the question is, what's the probability that if between the 3 cookies, A, B, and C, there's really no difference, they all taste the same, that 4 test persons testing each cookie come up with a difference that is as high as an F statistic of 7. So what we do is we look that up in a F table, and an F distribution always looks different depending on the degrees of freedom that we have. So let's say ours looks like this. So then what we need to find is we need to find our critical F. So what is our F critical? So if you want to reject the null, or if you reject the null at a significance level of 5%, we need to find the F where we have to the right 5% probability. So in Excel, the formula that you want to use is equals F and then inverse right tail. And then it says, we want the probability in the right tail. What's the probability? 0.05. How many degrees of freedom do we have in the numerator? That's 1. Degrees of freedom 1 is the numerator. So we have 3 categories minus 1, so that's 2. How many degrees of freedom do we have in the denominator? We have a total of 12 observations. And we need to subtract the number of categories. So 12 minus 3, so that's 9. And now we get a critical F statistic of, let's say, 4.3. It's good enough. So that means our critical value is here 4.3. But we see that our test F, our F test, now that's actually a 7, so it clearly falls into the rejection zone. But we could make a type 1 error because there's like a little bit of probability mass left to the right of an F statistic of 7, and that would be the probability that we made a type 1 error. So in this case, we can calculate the F statistic at the probability as using the formula F dot dist and then right-tailed, and then we want to know how much probability do we have to the right of 7 if I have 2 degrees of freedom in the numerator between the groups, and I have 9 degrees of freedom for within each group. So now we get 0.0, but if I add some decimal points, okay, so it's roughly 1.5%. So there's still a 1.5% probability that we made a type 1 error, meaning that we rejected the null, even though it is true. Okay, so the probability that we made a type 1 error is roughly 0.015 or 1.5%. Well, we can also visualize that graphically, so that is a little bit nicer than what I just drew. So our F critical is that green vertical bar where we have to the right 5%, but we can barely see it. And again, so because our actual test statistic is in the rejection zone, we reject the null that there's no difference between the cookies A, B, and C, so we rejected the 5% significance level. So, but we could have made a type 1 error, but anyhow what the result tells us is if there were no difference between cookies A, B, and C, so they were all the same, there is only a 1.47 or 1.5% chance that your observation stems from a scenario with no difference between the players or the cookies and the players. They all would evaluate them normally the same. So, but now you got a sample that suggests that H0 is not true, or we don't know if it's true, but it's very unlikely to be true. So therefore you conclude that it's more likely that the null does not hold. And again, here's our critical value of 4.26, where we have to the left 95% or to the right 5%. When it comes to an F statistic, there's also still tables as you can imagine. So here on this graph you see, for example, an F table that gives you the right tail probability. So we can use that to look up our critical F, and if you remember, we had 2 degrees in the numerator, so we go degrees of freedom in the numerator 2, and in the first column we have the degrees of freedom for the denominator, and we had 9. So we need to look into this array, which I now box in red. And then you see it gives you certain critical values like 0.1, that would be 3.01. Our value was 0.5, and here you see again the 4.26, which we also obtained using Excel. Okay, so now we know that our test statistic was actually 7. And so we have 2 degrees of freedom, and then we can see, well, the 7 is somewhat between the 25, the 0.025, so the 2.5% probability, and the 0.1 probability. But this is really an approximation, so we could tell from the table that there is a between 1% and 0.25% probability that we get the observations that we see in front of ourselves if there's presumably no difference between cookies A, B, and C. And I think I said that already several times whenever I look at those tables. I don't know how long we still work with those tables. You still find them in all the textbooks. People probably still use them to teach with them. But of course, what is much more convenient these days is just to look up values and probabilities using Excel. Okay, so this is our result. We reject the null hypothesis that there is no difference. And of course, what we do not know is where exactly the difference has occurred. But once you work, let's say, with real-world data, what you probably will not do is calculate the total sum of squares and the sum of squares within and between by hand, but you will just go to Excel. So now let's just see what we get if we replicate our result in Excel. So this is again our data. Okay, maybe make it a little bit smaller. And now we can go to data, data analysis. Okay, and then you see you have different ANOVAs. We want to focus only on a single factor, and there is also a two-factor with replication and two-factor without replication. So a two-factor ANOVA would be if, for example, I would additionally distinguish who the test person is, maybe if the test person is male or female. If I just look at those differences between male and female, in sum, it would be a two-factor without replication. But if I really list down what the females and males individually have, how they have evaluated the cookies, it would be a two-factor without replication. I don't think it's worth to cover this, because once it comes to two-factor ANOVA, it is probably more convenient to use just regression analysis and analyze everything there. And a one single factor ANOVA, what we did here, is definitely enough in order to get the idea of what ANOVA is and what analysis of variance is. But yeah, you could extend it to other scenarios too, but I'll just stay with a single factor. And yeah, so now let's run it. So we click on ANOVA single factor. And then it just says, okay, our data is grouped by column. So we have the values for A, B, and C. And our data has labels, which is cookie A, B, and C. Okay, so now we just highlight the A, B, and C and the corresponding values. And then, yeah, I just put the result here on the same page, maybe here. And then if you click OK, we should see the result. So now you see ANOVA single factor, A, B, and C. And we see the sum in each group and the averages, the 3, 4, and 8. We also get the variance. And then at the bottom you see the source of the variation. So we have the between group sum of squared of 56, the 36, the within group, the total 92, degrees of freedom 2 and 9, the mean sum of squares 28 and 4, the F statistic is F, and the p-value is 0.014, and if we round it, it's 0.05, and the F critical is also the same that we got. So 4.26. Okay, so now we know that we can reject the null, and yeah, this is how you conduct a single factor ANOVA. And if you ever encounter, let's say, regression analysis, you typically get also an ANOVA table as part of an output. And you should have a clear understanding now of how to conduct an ANOVA table. Okay, so that's it. And let's just stop here. And let's do some problem sets in the next video.